Okay, guys, so this is a Unit 2 atomic theory part of your final exam. We started this somewhere in mid-September, okay, or end of August. But if you have not already watched the Unit 1 final exam review over matter, you need to pause this video, go back and watch it, and then come back to this one, okay? You need to watch them in order because remember, chemistry builds upon itself, okay? So, let's go ahead and get started. Again, you're going to need paper in front of you, so let's get going. Now, remember, matter, okay, which is what we talked about in Unit 1, it's made up of anything that has mass and volume, okay? It's made up of these tiny things called atoms, all right? Atoms make up everything in the universe, okay? And these atoms are made up of 3 subatomic particles. So we're going to create a chart, okay? We have subatomic particles column. We're going to have talk about the position or location of those subatomic particles in the atom. We're going to talk about their charge. And we're going to talk about their size. Okay, so the first subatomic particle that we are going to talk about is the proton. Okay, now the proton symbol is a lowercase p with a positive sign as an exponent. Okay, the proton is located inside the nucleus, and you say, wait a second, isn't that like in a cell? Isn't that a biology word? Yes, we use it in both chemistry and in biology, but in chemistry, the nucleus is at the center of the atom, okay? So the proton has a positive 1 charge, so it's positive, and its size is 1 AMU. Now, an AMU, which I don't know why my pen is freaking out, but an AMU stands for an atomic mass unit. So it's essentially a unit we made up equal to 1 proton. Okay. Now, the next subatomic particle is the neutron. So let's go ahead and talk about it. Now, the symbol for the neutron is a lowercase n with a 0 as its exponent. Okay, and you'll find out why in a moment. It is also located in the nucleus. Okay, it has no charge, so it is neutral. Okay, that's why it's got that 0 as an exponent. It's got no charge, and its size is roughly the same size as a proton. It is 1 AMU. Okay, so all right, we've got protons, we've got neutrons. What's the next one? The next subatomic particle is the electron. Okay, now the electron symbol is an E with a negative as an exponent. It is located in what we call the electron cloud. Okay, and it surrounds the nucleus. And we will get into a little more detail about what that means when we talk about electrons themselves, but we're just doing a general overview right now. Now, the electron, as you might have guessed from its negative exponent, has a charge of -1. So it is a negative particle. And its size is roughly 0 AMU. And you're like, how? But doesn't it make up matter? And matter has volume and mass, so it must weigh something. And you're right, but that's because 1,680 something around there electrons weigh the same as 1 proton. So that means 1 proton, which is already tiny, 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 we can't even see it with our microscopes yet, is equal to almost 2,000 electrons. That's crazy. It's way too big, right? Exactly. Which is why essentially when we're figuring out the mass of how much an atom weighs, we don't really count the electrons. The protons and the neutrons are really the only thing that are going to affect the mass of an atom. Okay, so this is kind of our general overview here. So if you're not done copying this in your notes, just, pause the video and then press play when you're ready to keep going. Okay, so if you are ready, that must mean you're ready to move on. So we are going to separate these into three big components, okay? The first one, you've got it, is the proton. Okay, so we're going to talk about the proton first. Now, the proton is critical for the identity, okay, of an atom. The number of protons determines what type of atom it is, okay? And we use our periodic table to organize things, and it's organized by that number of protons, by its atomic number. So if you look at the periodic table, you're going to see a bunch of these squares, okay? And let's just take one for example that looks like this. All right. We're going to talk about what each of these things mean. Well, this 8 here is the atomic number, okay? And the atomic number tells us the number of protons, okay? And in a neutral atom, it tells us the number of electrons, okay? But that's only in a neutral atom where our protons and electrons are the same amount, okay? This O here is our element symbol. Okay, and they always start with a capital letter, and any additional letters will be lowercase. All right, so you can always tell if you're looking at a lot of elements, a lot of different atoms, if you see a lot of different capital letters. Okay, this right here is going to be our element name. Pretty self-explanatory, and we use our element name when we're trying to name compounds, things made up of multiple multiple atoms, okay? And then this number right here is the atomic mass, okay? And the atomic mass is the number of protons plus the number of neutrons. And you might be saying to yourself, Miss Nichols, I thought you said we only had protons and neutrons, and you can't have half of a neutron, so why do we have these decimals here? And this is because this number is a weighted average, okay? And we will get into that a little more when we talk about isotopes, okay? So keep that in mind for later. We will come back to it, I promise, okay? Now, so the main thing with our protons is that they're critical for the identity. We know that they're inside the nucleus. They are positive, okay? And they are used to organize the periodic table, okay? So protons always stay the same. Oxygen will always have 8 protons. Hydrogen will always only have 1 proton. Helium always only has 2. Okay, you can't change the number of protons without changing the identity of the atom. Okay, so we're kind of done with protons. Protons are kind of simple because they don't change. So what we are going to do is we are going to move on to our next spot about electrons. Okay, so electrons. Let's get into those. So we know that electrons are negative and they're located in the electron cloud. Okay, and you're like, Ms. Nichols, what is the electron cloud? Well, if we look at an atom, so let's say these are protons, okay, these are neutrons, they're kind of all in the center of the atom, okay, they're in this thing called the nucleus. Well, the atoms, okay, have the electron cloud around it. Okay, so let's say the red dots are going to be electrons. And the closer you are to the nucleus, the more likely you are to find an electron. Okay, And the farther away you get, the less likely your probability is. Okay, so our current understanding is called the quantum mechanical theory. And Ms. Nichols, that sounds really complicated, and that's because it is. Okay, it's essentially based on probabilities, but our older understanding of it was that at the center you had your nucleus. Okay, we have our nucleus at the center, so we're just going to make a big nucleus. We know it's made up of our protons and neutrons. And they said that you have rings around this nucleus. Now, we use this model as well. Okay, it's called the Bohr model, and it was named after this guy named Niels Bohr. Okay, and what he discovered was that these electrons are sometimes in specific areas more often. Okay, so we call each level can have a certain amount. So each level is called N. So N stands for energy level. Okay, so if you have N1, meaning the first energy level, as close to the nucleus as you can get, it can hold 2 electrons. N2 can hold up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right, so it can hold 8 electrons. And N3 can hold up to, let's see, 8 plus 10 is 18 electrons. N4 can hold up to, let's add 14 to that. So if we add 18 plus 14, we're going to have 32 electrons. Now, I'm not going to draw all those. And you're like, Ms. Nichols, I hear you counting these out loud. Why are we adding specific numbers? And that's because our electron shells are broken down into groups. So let's say we have our energy level. Okay, our energy level can be broken down at the largest level so let's say for N4, okay, it can be broken down into sub-levels. Okay, it can go down to sub-levels. Okay, now each energy level has a certain number of sub-levels, and they have different names. We have S, P, D, and F. Okay, so these sublevels, S, P, D, and F, hold a certain number of electrons. Okay, and that's because they are also broken down into these things called orbitals. Okay, so each sublevel, S, P, D, and F, has a certain number of orbitals. Okay, S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and I'm drawing them as boxes because you're going to see them as boxes later, and F has 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so we're going to call those boxes. So you have energy levels, okay, you have sublevels, S, P, D, and F, and you have orbitals within them, and then you have the electrons that fill them. Now, each orbital can hold only 2 electrons. So we have a total of 2 electrons in the S level. 3 times 2 electrons is a total of 6. D can have 10 electrons, and F can have 14. Okay, so you're like, well, how can I organize this? This seems kind of crazy. Okay, now remember, you have 7 energy levels. Okay, so with the first level, so N1 has just an s orbital, N2 has s and p, N3 has s, P, and D. And then in level 4, 5, 6, and 7, I'll have S, P, D, and F. Okay. And whether or not they're filled in, you'll also see when we talk in our next video about how these orbitals and sublevels and energy levels kind of affect the way we arrange our periodic table, which you know is our handy-dandy thing. So back to these electrons, okay? If we're looking, remember, they have these rings, but it's more like a cloud, which is why we call them electron cloud. They're negative, things of that nature, okay? Energy levels broken down into sublevels, S, P, D, and F, which can be broken down into orbitals. S has 1, P has 3, D has 5, F has 7. They can each hold 2 electrons. So that's how we figure out how many electrons can go on each ring or each energy level. Okay. Now, if we are looking at that, okay, we want to talk about something called electron configuration. And you're like, what is that? Okay, well, configuration just means how they are arranged. And we've kind of already seen that when we talked about how they are broken down. Okay, and so what this means is there are a few rules that we follow, but I'm mainly going to just show you as an examples. So if you have a periodic table in front of you, you're going to need one. But if you look at let's take beryllium, fluorine, for example. So if we look at fluorine, okay, we can look at its atomic number, and the atomic number of fluorine is 9, which means it has 9 electrons. That means when their electrons fill things in, they fill them in from the top or from the bottom down. That means you start at your first energy level, really close to your nucleus, and you slowly spread out. So let's draw that as our boxes. So if I'm talking about 1s, okay, the 1 is referring to my energy level. Okay, the S is referring to my sublevel, and the box is my orbital. And I'm going to draw arrows up or down. They're going to be my electrons. Okay, so I have fluorine is going to have 2 rings. Okay, so it has 1s available to it. It has 2s, and then it has 2p. And remember, I'm drawing P with 3 boxes because it has 3 orbitals available to it. So if fluorine has 9 electrons, it's going to fill in 1s first. And electrons have to have opposite spins. So you're going to have 1 electron up, 1 electron down. So I've used 2, I have 7 left. Well, now it's going to take a little bit more energy to get to 2s, and so it's going to fill in all of 2s. Okay, 2s has less energy than P, which is why it's going to fill that in completely first. Now, when we get to the P level, all of the orbitals inside the P sublevel are equal to each other. Okay, now they're more energy than 2s, but all 3 2p boxes are equal to each other. So the electrons are going to spread out first. They're going to say 1, 2, 3. Okay, so I still need 2 more. Right now I've got 7 filled in. So now they're going to go back in and fill in, and I'll have 1 empty space. Okay, now how these electrons are arranged affect the chemical properties. Okay, so the arrangement of electrons affects chemical properties. Okay, and we are going to see this a lot in our periodic table unit. But for example, because I have only 1 electron there, okay, it means it's going to be highly reactive. Okay, meaning it's going to really want to find something to give it that extra electron to fill it in. It's like, oh, it's the only one that's missing one. Okay, and we're really going to see that. We'll talk about it more in our periodic table, but this arrangement really affects the chemical properties. Okay, now we can also write this. You're like, drawing all those boxes every time? That seems crazy, and that's because, well, it is. Okay, now this whole image here, these are called orbital diagrams. Okay, diagrams meaning pictures. Okay, so if we're talking about the electron configuration, okay, we're actually talking about writing it out. Okay, and that is because the electron configuration for fluorine would look like this: 1s2, 2s2, 2p6. Okay, excuse me, 2p5. Sorry, where the 1, 2, and 2 are talking about the energy levels. The exponents here are referring to the number of electrons in each sublevel, okay? And the PS and S are your sublevels. So if we're practicing on a periodic table, which let's go ahead and pull one up. Had to pause the video to get my periodic table up, but let's go ahead and look at this periodic table. Okay, you're like, well, how is it arranged with all the things we've been talking about? Energy levels, sublevels, things like that. Well, with the periodic table, you can number each row, 1, 2, 3, 4, 5, 6, 7, and these two at the bottom are part of row 6 and 7. They belong here and here. Okay, but I'm going to erase that because it makes it look sloppy. Okay, those are our energy levels. So our rows are equal to our energy level. Okay, the periodic table is set up by our sublevels. These first two columns here in a periodic table are our sublevels. Well, yes, there are sublevels, but it's specifically the S sublevel. The rows over here are part of our P sublevel. The ones in the middle here are the D sublevel, and these over here are the F block or F sublevel. Okay, now one thing that you can take a note at is that within each one, okay, we know the S block can hold 2 electrons. Well, it has 2 columns. So this would be 1s1. Okay, it's on the first energy level. It's in subblock 1, has 1 electron. Helium actually goes in this section here for electron configuration. It's just in this row or in this column because it acts like all of those other ones because it's filled. But it would be 1s2. It's on my first row. It's in my S block. It's got 2 electrons. Okay. The ending configuration for lithium would be 2s1, 2s2. Boron would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and so on. Okay, now when you get to the D sublevel, that's when it gets a little different, right? So here would be 4s2, 4s1, 4s2. But when you get into the D sublevel, you subtract 1 energy level. Okay, and the reason why is because the in the D orbitals are so complicated and take so much high energy, they actually overlap with the 4s. So 4s, even though it's on a higher energy level, requires less energy than the 3D. So this would actually be 3D1 all the way to 3D10 for zinc. Okay, and then it would go back to the original 4p1 all the way to 4p6. Okay, so our periodic table is kind of like your roadmap, and the last part of your electron configuration would be kind of like its home address. Okay, you know exactly where it is because of its energy level, sublevel, and number of electrons. So which we know how many electrons it is or what electron it is based on its valence electrons. Okay, so that's another word that we are going to talk about here. Okay, we have valence electrons. Okay, now valence electrons are the electrons located on the outer shell, and they are responsible for chemical properties and bonding. So how bonding, which is, how reactions happen, bonding's forming, bonding's breaking, things like that. Now, if you're looking at your periodic table, each column has a column number. If I can get my screen to scroll. Let's see. Okay, back where I left off. The columns all have a number, so I'm going to erase some of this. That way we can see what's happening. But each column has a number. Okay, same as our rows. But what they tell us is instead of their energy level, these column numbers tell us the number of valence electrons. Okay, now remember, valence electrons are the electrons on the outer shell. So something in the first column would have 1 valence electron. Then the second column would have 2 valence electrons. And we kind of skip this D block here. And that's because they're on our third energy level, so they're kind of tucked in. Their valence electrons is dependent on the S block. Okay. And it can change. Everything in this center section, they're called transition metals because they transition all the time. They have a lot of weird rules. But 13, column 13 would have 3 valence electrons, and then 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and then starting with neon, it would have 8 valence electrons. Because helium only has 2, it has 2 valence electrons. It's completely filled up. Now, there's this thing called the octet rule that says all electrons are most stable. Okay, and I've used stability in terms of like happiness. So all electrons are most stable with 0 or 8 valence electrons. Okay, they need that outer shell to be full. Okay, and stability is talking about like they will not react very much. They're just going to be very chill, very calm. Okay, electrons are the most stable when they have 8 valence electrons. Okay, or they've lost all their electrons and now their inner shell is now their valence electrons, and it's essentially like they have 0 left in that outer shell that it was previously occupied. Okay, so that's dealing with electrons. But electrons are also how we deal with light. So let's talk about that. Okay, so when we're dealing with light, okay, light has this thing called particle duality. Okay, now in particle duality, dual means 2, and this is because it behaves like a particle and a wave at the same time. Okay, and you're like, well, what is the difference? Well, a bundle, we have this one word called photons that you're going to hear me use. Photons means a bundle of light particles. All right, and there was this guy named Max Planck. He was doing these experiments, and he noticed, well, he was like, okay, well, light has to be a wave, right? It moves, all these things, just like a wave. But then he realized that it also behaved like a photon in certain instances. And so with this, he had to come up with this idea of light particle duality. Okay, so before we can really talk about it, we have to talk about the parts of a wave. So a wave looks like this, okay? it's symmetrical. Now, mine is not, but that's because I'm not a very good artist. But we're going to talk about a few different things. The top of the wave is called the crest. The bottom of the wave is called a trough. The distance from the top of the wave to the center, or the bottom to the center, is called the amplitude. Okay, you can measure it from either way. And the distance from crest to crest, or trough to trough, is called the wavelength. Okay, now wavelength has this Greek symbol that looks like a kind of curly upside down Y. And we use that because wavelength tells us how, I guess, the distance, okay, how long it is, okay? So when you're talking about like with your radio, if you know you're turning to 98.5, you're talking about your frequency, and you're like, well, what is frequency? Frequency, okay, frequency measures the number of waves per second. Okay, now, so that means if you have a long wavelength, you're going to have a low frequency, okay, because you're not going to have as many complete waves pass. Whereas if you have a short frequency, you're going to have a high, or excuse me, if you have a short wavelength, you're going to have a high frequency. And this ends up creating this thing called the electromagnetic spectrum. Okay, and with this electromagnetic spectrum, okay, it's basically how energy as light, okay, exhibits that wave-like behavior. Okay, it goes from the radio waves, have the longest wavelength, okay, and the shortest frequency, and it goes all the way till you get to gamma rays. Okay, and gamma rays have really short wavelengths, which means they have a very, very high frequency, very, very high energy. Okay, and visible light, kind of somewhere in here. And this is where you get all of your colors. You get Roy G. Biv. Okay, now kind of in between these, you have microwaves, you have IR, you have infrared, you have your ultraviolet light, so UV light. You also have your X-rays in here, okay? Now, this is kind of just talking about how energy moves through all of that. So we know that light behaves like a wave, like this, but light also behaves as a particle, okay? It can stream in those tiny bundles. And if it was only a wave, it would only act like a wave. But if it's light, okay, we got those photons. It can also shoot out like pockets or bundles of light. Now, the reason why he figured this out is he discovered how electrons emit energy in the form of light. So let's bring it all back to our electrons that we were talking about. If we have our nucleus, okay, this is going to be our nucleus here. Okay, we're going to make sure we just label that our nucleus, okay, and we have those rings. Okay, well, what happens is when light is emitted, let's say we've got these electrons here, okay, when energy is absorbed, okay, let's say energy comes in, so this is energy, capital E, comes in, this electron gets excited, okay, it's absorbed energy. Now we know that each energy level takes a certain amount of energy, so if I have a lot more energy, it causes my electron to jump up. So now my electron is at this new energy level, okay? So it's absorbed energy. Well, that's unstable, okay? And that state is called the excited state. So the excited state is where the electrons are in a higher energy level because they absorbed energy. Okay, but it's unstable. And so what happens is they have to return to their ground state. So this is their original energy level. So that means this electron is going to go back to its ground state. But when it goes back to its ground state, it is going to release light. Okay, it's going to release energy. Okay, it's releasing energy in the form of light or a photon. Okay, now this light is emitted at different wavelengths. Different wavelengths. Remember, the upside down Y is a symbol for wavelengths. And so because they are different wavelengths, we see different colors. And you're like, what? This is crazy. Yeah, this is how neon lights happen. So as energy is absorbed, electrons move from their ground state, their original energy level, to their excited state, which is a higher energy level because they've absorbed that energy. But because it's unstable, they're going to return to their ground state by releasing energy in the form of photons as light. Okay, now this creates what we call the atomic emission spectrum. Okay, and this is essentially the fingerprint of an atom. Okay, and what that means is each atomic emission spectrum is unique to each atom. So, for example, I have beryllium, Be, beryllium on its spectrum, which it would just look like a little box, okay, and it would have discrete lines. So beryllium has kind of a blue line, and then it has a green line, and then it also has some purple lines down here, like one purple line and kind of a dark bluish line. Okay, it's discrete lines. You can't see all of the colors, Roy G. Biv. You can't see just an entire thing um, of all the light, just these discrete outputs, and that's because those electrons are moving up to certain energy levels and going back down to certain energy levels. So they can only release a certain amount. Whereas titanium, okay, if we were to have the atomic emission spectrum of titanium, titanium has kind of a pale blue line here, and it has kind of a bright green line, okay, and then it's got a sort of goldy orange color, then a really orange. Whoa, don't know what's happening there. So let's get back to it. It's got kind of a darker orange line, and then it's got like a red line here. So you can see that they're all unique. They have a different number of electrons because they have different number of protons, and so those electrons absorb energy and can go to different states. They all have different sublevels, energy levels, orbitals, and they can all move around. That's why it's unique for every single element. Okay, so that's the emission of light. Okay, so we've essentially talked all about protons and we have talked about our electrons. But there is that third subatomic particle, which, even though it's 40 minutes in and we've barely talked about it, does actually have a pretty big importance. So let's talk about the neutron. Oh, one thing. Oops, let's never mind, jumping too far ahead. We still need to talk about the electron because there's this thing called ions. If I could spell ions. Okay. Now ions have a different number of electrons than a neutral atom. Okay, now in a neutral atom, the number of protons is equal to the number of electrons. Okay, but what if your number of protons is greater than your number of electrons? Well, in this case, you have more positive charges, so you are an overall positive charge, whereas neutral has no charge. Okay, and that means we would call this a cation. Okay, now the way I remember this is cats have paws and cations are positive. Yes, that's very corny, but it helps you remember it. But what if we have the opposite? What if the number of protons we have is less than the number of electrons? Well, then you're going to have an overall negative charge, okay? Because you have more negative electrons, and these are called anions, okay? Cats have paws, so cations are positive, whereas anions are negative. Okay, so now that I didn't forget that, let's go back to our neutrons. So these neutrons, yay. Remember, neutrons are in the center of the atom in the nucleus, and they have no charge, but they do have mass, and that is why they're important. So let's look at the word isotopes. Isotopes are when you have a different number of, you guessed it, neutrons, okay? You have a different number of neutrons. Now, this means that you could have something, let's take carbon for example. So carbon has a few different isotopes. It has what we call carbon 12, carbon 14, and carbon 16. And you're like, okay, well, I see the different numbers, but what is that? Well, carbon is the name of the element, and 12, 14, and 16 are the mass number. Okay, so all three of these are the mass number. Now, remember, if you look at the atomic mass, right, your mass number is your protons plus your neutrons. And you say, well, carbon always has 12, not 12, always has 6 protons because its atomic number is 6. Now, it can't be carbon if it doesn't have 6 protons. It would be something else. So the 6 protons never changes, okay? But for our mass number, that would mean our number of neutrons for carbon 12 is equal to our 12 minus our 6 protons, which would give us 6 total neutrons. That means over here, the number of neutrons is equal to 14 minus 6, which gives us 8 neutrons. 8 neutrons. Let's add that symbol there. Well, I don't know why it keeps doing that. My computer is freaking out, and I apologize. 9 neutrons. And then over here, 16 minus 6 will give us 10 neutrons. Okay, so they all have a different number. Now, these are all found in relatively different abundances. If you look at the periodic table, okay, and you look at carbon, carbon has 6, and the number at the bottom is 12.011. Okay, and you're like, well, we know that we can't have a like half of a proton or a neutron, and that would be correct. Okay, so but what we do have is a different abundance of the isotopes. Okay, and so because we have a different abundance of the isotopes, okay, they're available in different percentages. Carbon 12 is the most abundant, okay, which is why the number on the periodic table is most similar to 12. Carbon 14 is the next highest, okay? And then carbon 16 is the smallest percentage, okay? And this creates a weighted average. So if we want to look at this weighted average, okay, in order to calculate the atomic mass, so remember, let's just write this down. The atomic mass is a weighted average of all isotopes. Okay, now if you have a higher percentage, then you are going to be more accurately or more highly represented in your atomic mass. So let's take carbon, for example. Now, my percentages are not going to be correct. I haven't looked them up. I'm just kind of making them up. But let's say we have carbon 12 is, let's say, 96% of all the carbon in the world is carbon 12. And then let's say carbon 14 is 3%, and carbon 16 is the remaining 1%. Okay, we would calculate this into the weighted average. So what we would do is we would take the mass and multiply it by our percentage, and to multiply it by a percent, you have to convert to a decimal. We have 12 times 0.96, 14 times 0.03, and 16 times 0.01, and we would multiply all of these numbers. So if we take our calculators out, 12 times 0.96 is equal to 11.52. 14 times 0.03 is equal to 0.42, and 16 times 0.01 is going to give you 0.16. And then we add them all together. So if we do that, 11.52 plus 0.42 plus 0.16, we get 12.1 AMU, atomic mass units. Okay, this is pretty close to what is on the periodic table. It's 12.011, but considering I made up my percentages, I was pretty close. That's how you would calculate your weighted average. It's also similar to how you would calculate your grade in chemistry. We know that our tests are worth a more percentage than our classwork grade, and our final exam is worth a certain percentage. You would figure out your total grade in each category, multiply them by their weight, add them together, and that's how your final grade in chemistry class is calculated. So let's also talk about how neutrons, okay, affect the nuclear stability. Okay, so when atoms are unstable, so unstable atoms, okay, this usually happens when their nucleus gets too big. And you're like, well, what do you mean too big? Well, if I have 46 protons and they are all around each other, okay, positive things repel other positive things, okay? It's kind of like two ends of the magnet. So the neutrons, okay, neutrons keep the peace. They keep the peace in the nucleus, which is why something with as high as 46 protons, which is palladium, has almost double the amount of neutrons. Okay, it's because it requires a lot of neutrons to keep the protons from completely repelling each other and breaking apart the nucleus. Now, when the nucleus does break apart, because this happens with our heavier elements, okay, we call this radiation. So radiation is when the nucleus emits particles and usually energy as well to become smaller and more stable. And there is three main types of radiation that we want to talk about. So let's go ahead and create a chart. So on our chart, we're going to have the types of radiation as our main column. Okay? And there are 3 types. We have alpha, we have beta, and we have gamma. Now, you should remember these from physical science. Also, you should remember them from learning them back in August and September. So, with alpha, beta, gamma, okay, they have a particular symbol. They have a certain composition or what they're made up of, okay, what their particles that they emit are, and what they can be stopped by. Because radiation, you're like, oh, Miss Nichols, I normally hear that when you're talking about like cancer or things that are killing you, and that is true, okay? But sometimes radiation can be good or it can be easily stopped. So let's look at the different types. So alpha, okay, alpha particles, the symbol is kind of like this little fish, okay? Or it's the same as a helium atom. Now remember, with this type of notation, the 4,2He, you have your symbol, your mass number is the top, and your atomic number is the number on the bottom, okay? It is made up of 2 protons and 2 neutrons, and it can be stopped by your skin, it can be stopped by paper, and it can be stopped by clothing. Now, this is because it has the smallest energy, okay? Doesn't have a lot of energy, okay? Beta particles look like this weird bee, and it is made up of 1 electron, which is why its symbol has 0 mass. It's got a -1 mass number or atomic number, and the symbol E for electron. Now, it has a little bit more energy, so it needs to be stopped by things like aluminum foil, plastic, wood, or glass. Okay, now gamma rays. Gamma rays, their symbol is kind of this curled Y, and they are pure energy. Okay, so it's straight up energy. So in this case, they need to be stopped by things like lead, concrete, and earth. I'm talking about like dirt, like meters of dirt, like a lot of it. Okay, and if you've ever been to the doctor when you've had an x-ray done, they put on a lead, right? Like if you're getting your leg or your arm x-rayed, they put generally that thing over your chest, and that's to prevent extra x-rays, which are pretty close to gamma rays in terms of strength, through your body, right? They want to limit how much of that you see. So we can see how these are arranged. Now, when we talk about these kinds of things, we need to talk about transmutation. Okay, and transmutation is when an atom changes into another by emitting radiation as a particle. Okay, you can have alpha, beta, or gamma decay. All right, so it's when we say an atom changes into another, we talk about decays because it gets smaller. Okay, so with alpha decay, right? If we start off with polonium, which has the atomic mass of 214 and has an atomic number of 84, and the symbol for polonium is PO, right? And it undergoes alpha decay. What happens is it's going to emit an alpha particle. So 42He, it's going to emit a helium. Now when it does this, you can say 214 minus 4 gives you 210, And 84 minus the 2 particles that went in the helium is 82. And if you look at number 82 on the periodic table, it's Pb, it's lead. So polonium decayed into lead by emitting an alpha particle. Okay, so this is our alpha particle, which I'm having trouble spelling today. So that looks like terrible handwriting, but that says alpha particle. Now, what about if we have beta decay? Okay. Well, it's very, very similar in that you just release a beta particle. So let's say we now have lead, but a different isotope. It's 209 mass. It's got 82 protons, so it has one less neutron than lead 210. And it emits a beta particle, which is an electron. Well, when it does this, we can say 209 minus 0 is 209, so its mass stays the same, but 82 minus a negative 1 means that it gains a proton, 83. So number 83 on the periodic table is bismuth. With this decay, all things decay over time, right? We can see things break down. And so with that, scientists use what's called its half-life to measure how old certain things are. So our half-life is the time it takes for half of the mass to decay or disappear, okay? And so it can range from really like a fraction of a second to billions of years, okay? And so if we look at a graph, okay, half-life, the graph on the y-axis would be the amount or grams remaining, and on the y-axis it would be time. Okay, now over time things start to decay. So your graph is going to look kind of like that. Now if we look at, for example, carbon 14, which is usually in all like pottery and bones and things like that, and so archaeologists use carbon 14 as carbon 14 dating, used to figure out how old things are. Well, the half-life of carbon 14 is 5,730 years. That's how long it takes for one half of carbon 14 to decay. So if we start off with 10 grams, okay, the time it takes to decay into only having 5 grams would be 5,730 years. If it were to decay into 2.5 grams, that would take an additional 5,730 years, which is why, because this half-life is so long, we use it to measure how old things are, because usually we're not measuring things that are over 10,000 years old. But you can see if it started off with a lot of carbon, we might be able to still determine how old it is, which is why most living things are made up of carbon. And so we use that to help us determine. Now, when we're talking about decay still, there are a few things we need to talk about. We need to talk about the difference between fission, and we need to talk about the difference between fusion. So fission is when the nucleus breaks apart. So we would have one nuclei break apart into 2 smaller nuclei. Whereas fusion is when the nucleus of 2 things combine. So you would have 2 smaller nuclei come together to form a bigger one. Okay. Now fusion is how all elements heavier than probably around like cobalt, I believe, are made. They're made in the sun, well, in stars like the sun. And for example, if you were to have helium Okay, if you had 3 heliums and you fused them together, like so, you would form 4 plus 4 plus 4 is 12, 2 plus 2 plus 2 is 6, and number 6 on the periodic table is carbon. Carbon 12, one of the most abundant elements in the earth. Okay, it's what a lot of things are made up of. Things are fused, they come together. Now, fission is how we get things like nuclear energy, okay? Nuclear bombs. You take something and you break the nucleus apart. When you force a nucleus, like the hydrogen bomb, you force a hydrogen nucleus to break apart. Now, in order to do that, you have to put a lot of energy in it, but it releases a ton of energy in the process, and things start to break apart. Okay, so now, if I'm not mistaken, we are at our final thing. We are done. So you might want to look into how to do half-life calculations and things like that, but this video is already an hour. So let's stop, refresh our brains, come back for Unit 3.